Welcome to The Explainer. Today, we are diving deep into a world you probably never think about, but one that your entire digital life depends on: electronic timing. We're going to uncover the secret to how everything from 5G to self-driving cars stays in perfect sync, in a world where even the tiniest wobble can cause a total system meltdown. All right, here's how we're going to break it down. First, we'll talk about this quest for perfect time. Then we'll meet the bad guy that's always trying to mess things up, phase noise. After that, we'll reveal the awesome solution, a real jitter cleaning machine. We'll see why it's a battle of quartz versus the world. And finally, we'll tie it all together to show you why this precision stuff really matters. So let's jump right in. The quest for perfect time. You know, at the very core of our digital world, there's this fundamental need for a steady, unwavering heartbeat in every single piece of modern tech. I mean, think about it. 5G networks, giant data centers, self-driving cars, besides being super advanced tech, they all share this invisible backbone. It's an incredibly precise and stable clock signal that basically choreographs their every move. Without it, they just wouldn't work. Period. Every single one of these things, from the phone that's in your pocket to the complex servers running AI, relies on a little component called an oscillator. It provides a stable frequency, think of it as that reliable tick-tock for all their operations. But what happens when that heartbeat gets a little shaky? And that is where we meet the villain of our story. It's this subtle but incredibly powerful enemy called phase noise. This is the absolute nemesis of precision timing. So what is it, really? Well, put simply, phase noise is the wobble or the jitter in a clock signal. Instead of a perfectly steady tick-tock, you get a signal that's just a little bit unpredictable from one moment to the next. Imagine a clock hand that's supposed to sweep smoothly, but instead it just kind of jitters randomly. That's phase noise. And this tiny wobble, it has huge consequences. In communications, it messes up the data, leading to way more errors. That's your bit error rate going up. It can cause network links to fail entirely. And in high-precision systems like radar or GPS, it raises what's called the noise floor, basically making it impossible to see the faint signals you're actually looking for. So, you see, taming this noise isn't just some small improvement. No, it is absolutely essential for the reliability and the quality of our most advanced electronics. The big question is, how in the world do you fight something so small and so random? Well, that brings us to the really ingenious part, the jitter cleaning machine. Engineers came up with this brilliant system that actually fights all that noise, using a simple crystal and a clever loop. Meet our hero, the phase-locked loop, or PLL. It is just an elegant piece of engineering. It doesn't just filter a noisy clock signal. Oh no, it's much smarter. It looks at the average frequency of that messy input and then generates a brand new, squeaky clean, and incredibly stable signal, all while totally ignoring the fast, jittery noise. And right at the heart of this hero system is our main character, the voltage-controlled crystal oscillator, or VCXO. Its superpower comes from a tiny, perfectly cut piece of quartz. It acts like an ultra-stable reference, kind of like a perfect tuning fork that the PLL can listen to and copy. And this graph just shows the magic perfectly. Look at this. That purple line, that's our noisy, jittery input clock. It's got a wobble of over 7 picoseconds. Then the PLL, using that stable VCXO as its guide, generates the clean green line. Look at that. The jitter is down to just 218 femtoseconds. A femtosecond is 1/quadrillionth of a second. It's just mind-bogglingly fast. To put that into perspective for you, this system slashes that timing wobble by more than 30 times. The PLL literally washes away the noise from the input signal because it's locked onto the pure, clean timing reference from the VCXO. It is an incredible feat of signal purification. So, what is the secret sauce here? I mean, why quartz? It's a mineral you can literally find in sand. What makes it the go-to material for these super high-performance oscillators? Well, the answer is in the unique physics of quartz. First, it has this cool property called the piezoelectric effect. Basically, you zap it with a little voltage, and it vibrates at a very precise frequency. Second, it has an insanely high quality factor, or Q. All that means is it can vibrate for a very, very long time with almost zero energy loss. It's like a bell that rings with a perfect, pure tone for minutes after you strike it. That's what we want. Now, this brings us to a really interesting modern comparison. You've got these newer silicon-based MEMS oscillators. They're tiny and they're super tough. But quartz still wears the crown for any application that needs the absolute lowest phase noise and the highest signal purity. When you need the cleanest possible signal, quartz is still the undisputed gold standard. Okay, so let's bring this all back down to earth. Why does this obsessive quest for a perfect, jitter-free clock matter so much in the real world? Well, this technology is the hidden foundation of our modern world. Take 5G networks. They encode data using complex methods like QAM, where information is packed into both the size and the phase of the signal. Any phase noise, any jitter, directly messes that up. It increases what's called the error vector magnitude, or EVM. It's like trying to read a sign, but the letters are all blurry and jumbled. That's what phase noise does to data. And in radar, a low-noise clock is what lets the system pick a tiny, faint signal from a target miles away out of the background noise. It's the hidden hero in so many critical systems. And that really leaves us with a fascinating thought to end on. As our ambitions keep growing, we want faster data, smarter cars, more and more connected devices. That demand for even more perfect, more stable timing is only going to get more intense. And that's going to keep pushing engineers to make these unsung heroes of the digital age even better.